Let's look at alternating series. Sometimes you'll get a series that looks like this, in which case you can rewrite this as the sum as n goes from 0 to infinity of minus 1 to the n times 1/2 to the n. Now you see that if I didn't have this minus 1/2 in here, we'd have a geometric series of r equals 1/2. I can also see that it is a geometric series of r equals minus 1/2. So whenever you have this minus 1 to a power, we're going to call that an alternating series. Now there are two ways you can have an alternating series. One is with the odd terms being negative, and the other one is with the even terms being negative. So if you have an alternating series of the form, the sum as n goes from 1 to infinity of minus 1 to the n of a sub n, or the sum as n goes from 1 to infinity of minus 1 to the n plus 1 times a to the n, then this alternating series converges if the limit as n goes to infinity of the nth term goes to 0, and if you can show that a sub n plus 1 is less than or equal to a sub n for all n. So basically the terms are getting smaller and they're monotonic. So let's look at this series right here. The sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 1 over n. Now the limit as n goes to infinity of 1 over n is indeed 0. And now we need to show that a sub n minus 1, a sub n plus 1 is less than or equal to a sub n. So, and we're only looking at the positive terms, so 1 over n plus 1 is less than or equal to 1 over n. You can see this is a true statement, but we're going to get to a correct mathematical statement. So this is true. Therefore, by the alternating series test, the sum as n goes from 1 to infinity of minus 1 to the n plus 1 of 1 over n converges. Now please note, this is basically the harmonic series with the minus 1 to the n plus 1. So while the harmonic series diverges, when you have this alternating part, now it converges. Let's look at the sum as n goes from 1 to infinity of n divided by negative 2 to the n minus 1. So let me look at, first I want to look at only n greater than 1. So I've got 1 over 2 is less than or equal to n over n plus 1. So I've got is a true statement. So I've got 2 to the n minus 1 divided by 2 to the n has got to be less than or equal to n divided by n plus 1. So cross multiplying, I've got n plus 1 times 2 to the n minus 1 is less than or equal to n 2 to the n. So I've got n plus 1 divided by 2 to the n is less than n over 2 to the n minus 1. So what this tells me is a to the n plus 1, which is n plus 1 divided by 2 to the n, is less than or equal to n divided by 2 to the n minus 1, which is a sub n. Now, let me look at the limit as x goes to infinity of x divided by 2 to the x minus 1. I'm going to use L'Hopital. So this is the same thing as a limit as x approaches infinity of 1 divided by the log of 2 times 2 to the x minus 1, which is indeed 0. Therefore, by alternating series test, my series sum n goes from 1 to infinity of n divided by minus 2 to the n minus 1 converges. Now the alternating series test doesn't always work. Suppose I look at this series right here, and a sub n is n plus 1 over n. The limit as n goes to infinity of a sub n is the limit as n approaches infinity of n plus 1 over n, which is 1. And therefore, because the n term doesn't go to 0, we know this term, the alternating series test fails. And as a matter of fact, it turns out this entire series diverges. Similarly, if we look at this function right here, the limit as n goes to infinity of a sub n is indeed 0, but if you look at the second condition, which is a sub n minus 1 is less than or equal to a sub n, that is not true. So it turns out that the alternating series test fails here as well. You can't make this direct comparison. So the test fails